Hello students, and welcome to this lesson on properties of rational functions. Previously we have discussed a very specific function. We discussed the function y is equal to 1 over x, and that was our reciprocal function. So our reciprocal function was y is equal to 1 over x, and we learned how to transform that function, and we learned how to graph asymptotes from that function. Now we're going to see that the reciprocal function is part of a larger family of functions called rational functions. So today we will define rational functions and discuss vertical asymptotes using our journal notes and practice problems. First, let's define rational functions. A rational function is a function of the form Rx is equal to Px divided by Qx, where P of x and Q of x represent polynomials. The domain of a rational function is all real numbers, except for those values that make the denominator, Q of x, equal to 0. So what we're saying is that in a rational function, it's going to be all real numbers except for anything that will cause this to equal 0. And that makes sense, right? Because we have division here, and you can't divide by 0. So this is very similar to the domain of our reciprocal function, where we couldn't have a 0 in the bottom, and that was our restriction on our domain. Alright, so some examples of rational functions are listed. So you could have a quadratic function over a linear function. You could have a polynomial of power 0 over a quadratic function. You could have a quadratic function over a linear function, or any other combination of polynomials. So remember that a polynomial is anything that has an x in it or doesn't have an x. It's a string, right, where you have multiple numbers and multiple variables strung together, and you have a single variable. So you would say something like y is equal to, or f of x is equal to x cubed plus x squared plus 3x. That would also be a polynomial. So it's really just anything that's got a series of x's added together like this. So first what we want to do is learn how to find the domain of a rational function. So let's see what that will look like. So from our above definition, we know that the domain of a rational function is where q of x will be equal to 0 is the only excluded point. So other than that, it's going to be all real numbers. So let's figure out what our domain restrictions will be on these example problems. So we know that q of x is going to be the denominator in each case. So what we're focusing on is what will make the denominator equal to 0. Alright, so for example 1, we see that if we set x plus 4 equal to 0, then x is equal to negative 4 is going to be the number that will set our function equal to 0. So what we would say for this function, if I were to write the domain, I could write it one of two ways. I could say that the function goes from negative infinity up to negative 4, then excludes negative 4, and goes to infinity. So what we're saying is that we will approach the number negative 4, but then we will just skip it. Or another way that I could write this is I could write x belongs to R such that x is not equal to negative 4. So that's another way that I could write the domain. So both of these are valid ways to write the domain. So this is going to be interval notation, and this is set notation here. Alright, so for the second one, I'm going to write it in interval notation. And what we'll see is x is minus 2 is equal to 0, so we get x is equal to positive 2, and so that's going to be where my domain cannot be, so we'll say that my domain is equal to negative infinity up to 2, and then I'm excluding 2. Remember what this symbol means here is that we're going to exclude the number, and then we go from 2 to infinity. So that'll be my domain in that case. Down here I'm going to say in set notation. And so this is a little bit more interesting. So now I have x squared minus 9 is equal to 0. Well, remember, this is factorable, so I get x plus 3 and x minus 3 is equal to 0. So what I'll find is that x could be 3 or x could be negative 3. So if I were to write the domain in set notation, what I'd find is that x belongs to R such that x is not equal to 3 or negative 3. Alright, and then finally we'll do the same thing for this last example. So we have x squared minus 2x minus 15 is equal to 0. So we're going to want to factor this. So let's think of two numbers that will multiply to give me negative 15 and add to make me negative 2. Well, maybe x minus 5 and then x plus 3 is equal to 0. So then you get x is equal to negative 3 and x is equal to positive 5. So what we could say here is that my domain is going to be equal to, and I'm going to go ahead and do set notation again here because it's a little bit easier. So x belongs to R such that x cannot equal negative 3 or 5. So that'll be my answer. So just like you guys saw before, this domain has a relationship with a graph, right? And there's a very specific thing that will be graphed because your domain has this restriction. So let's go ahead and discuss what that will be. So the item which is being created by my domain, by that thing where I cannot be equal to it, is going to be my asymptote. And remember, your asymptote is a boundary line that a rational function approaches but never crosses. And you guys have encountered these with your reciprocal functions. Specifically, a vertical asymptote exists for any value of x that makes the denominator 0 and is not a value that makes the numerator 0. So, a vertical asymptote, what we'll find, is almost the exact same thing as your domain restrictions in most cases. So let's go ahead and just remember, so if I'm trying to draw a graph here and I'm thinking about my asymptotes, remember that these were just those imaginary lines that my curves kind of ran across, but I never was able to touch. So you guys saw these with the reciprocal function, and we'll start seeing them more and more with these other functions. Alright, so for example 5, we're going to go ahead and verify and make sure that we're going to determine our asymptotes. And a little hint here is just look at the domain and make sure that, that it's kind of matching up with what your domain will be. So first, we want to, in example 5, factor this out. So this is going to become x minus 4 and then x plus 4 over x plus 5. And we know that the vertical asymptote exists for any value of x that makes the denominator 0 and is not a value that makes the numerator 0. So here we'll see that the value that will make the denominator 0 is x is equal to negative 5, right? So that's my domain restriction. And so we see that it does not zero out either of the items up here. So that's the important part here, is that these will not become 0 when the denominator is 0. So my numerator is still positive, or still exists, but my denominator has become 0. So we can say that my vertical asymptote is x equals negative 5. So we see that the vertical asymptote and the domain have a very, very high level of correlation. Alright, so for example 6, first you want to factor it out, right? So factoring is going to become very important again. Remember your box method or your x method, so where you take your two numbers, right? So in this case it would have been negative 1 and negative 6 for the top, and you want two numbers that will multiply to give you negative 6, and you want to find two numbers that, and those same two numbers will need to add to make negative 1. So what I determined is that it would have to be negative 3 and positive 2. So that was for the top, and then I did the same thing for the bottom. And so I said, okay, well, I need two numbers. They're going to multiply to make 12, and they're going to add to make negative 7. Well, that sounds like negative 3 and negative 4. All right, so now we need to make sure that we know every number which will cause the bottom to go to 0. So we have x is equal to positive 4 and x is equal to positive 3. So those are both places where the denominator will be equal to 0. Now, we also have to see which of these numbers will cause the numerator to go to 0. And what we see is that we've got x minus 3 and x minus 3. So what that means is that the numerator will be 0 when the denominator is 0. So that means that this doesn't meet our condition for a vertical asymptote. It must make the denominator 0, and it does not make the numerator 0. So we can go ahead and cross out x is equal to 3, and so we can say that our vertical asymptote is x is equal to 4. All right, so that's as far as we're going to go today. So for your assignment, what you've got in front of you is a worksheet where you're going to be identifying the range and domain of these functions. You're also going to be finding the vertical asymptotes of things. So what I'd like you to do is go through these 12 problems and identify all of the vertical asymptotes first. So I know it is asking for the vertical and horizontal asymptotes, but go ahead and go through these 12 problems, identify the vertical asymptotes. So that's going to be your assignment today. All right, if you have any questions, go ahead and ask me during class, and then make sure that I stamp for your reflection. And your reflection today is that in 1 to 2 sentences, you will answer the following. How do you find the vertical asymptotes of a rational function? Tomorrow, what we'll be learning about more is the horizontal asymptotes and those situations where we had a term in the numerator and the denominator that were both 0, and we'll see what those are as well. All right, have a wonderful day. Let me know if you have any questions. Goodbye.